So hi, everybody. Welcome back to this last session of today. So this is the last talk of today. We have Anand here with us. He will give the first part of a 3-talk series. The other 2 talks will follow tomorrow, and he'll tell us a bit about their recent result on MIP star equals to RE. And just to reiterate for anybody who may be joining for the first time this session, if you want to ask a question during the talk, you can, if you're an attendee, you can type it in the Q&A and I will tell Anand what your question is. Or if you prefer to talk to using your microphone, you can also raise your hand and then we can give you the opportunity to speak. So, well, the floor is yours.
Okay, thanks for the introduction, and also thanks to the organizers for setting up this workshop. And also thanks to Andrea for the previous talks. I think this really laid a lot of the groundwork for what I'm going to talk about here. So hopefully I won't be repeating too much. Okay, so this is the first talk in a series of 3 talks on this work showing MIP star is equal to RE with my co-authors. And so the first talk is going to focus on a part of this called the quantum low degree test. So let me start with just a little bit of background on sort of the problem. And good. So in the previous talk, Andrea already sort of introduced this model, but let me just review it for people. So in the setting, we're talking about what are called non-local games in the quantum information literature and the associated quantum complexity classes. So a non-local game is a setup where you have a classical verifier that gets to communicate to 2 parties, which are called provers. So these are the parties Alice and Bob in this diagram here. And during the game, sort of the Alice and Bob are spatially separated, so they cannot communicate. The verifier will come up with 2 random questions according to some distribution and send a question to Alice and a question to Bob. And then Alice and Bob will have to each compute an answer to their question and respond and give it back to the verifier. Then the verifier will decide whether they've won or lost based on some predicate. So, this is the basic setup you have in a non-local game. And sort of the thing you might study here is sort of what are strategies that the 2 players, Alice and Bob, might use to maximize their probability of succeeding in the game. So the quantity we call the game value is just the supremum probability over all the strategies they could use. So they could be classical, in which case their strategy consists of, say, shared random bits or some other shared classical information that they agree on in advance. Or they could be quantum, in which case they're allowed to share a quantum state with some entanglement, and they can perform measurements on that state when they're playing the game. So there's this classical value, which is the maximum success probability when they're playing classically, and there's the quantum value, which is the maximum success probability when they're playing with shared entanglement. So that's the basic setup for these non-local games, and the intuition that you want to have for all these things is that you should think of the players as provers that are trying to certify something to the verifier. So in Andrea's talk and in this talk, we'll see that often what they want to certify is some physical property of the states that they share. They want to certify that they share a particular quantum state and that they're applying certain measurements to it. But in the complexity setting, what this turns into is that you can think of them as trying to certify to the verifier that the answer to a certain decision problem is yes. So this is the setting that you have in interactive proofs. And so you can define complexity classes associated with these games called MIP and MIP star for multi-prover interactive proofs. And the star indicates the version with entanglement. So these are the classes where you have either quantum players or classical players, but they're trying to convince a verifier that for a given decision problem, that the answer to that is yes. So a problem is it has a protocol in say MIP star if for every yes instance, if there's some game that the verifier can play with these provers, such that for every yes instance, there's some way for the 2 provers using their entanglement maybe to convince the verifier to accept, to win with high probability. And for every no instance, there's no way for the provers to win in the game with high probability. So that's the basic setup. And in the sequence of talks, we're going to basically tell you about work that characterize the complexity of this class. So just to give you a little overview, here's a little diagram of complexity classes. So here on the left, we have a bunch of things that are all sort of like different kinds of problems that are computable, but maybe in varying amounts of time or space. So and in particular, you have the classical class that came out of considering classical provers here. So an old result in complexity theory is that MIP is equal to NXP. On the other hand, in this diagram, I have on the other side, I have this class RE, which is recursively enumerable problems, and that's the class for which the halting problem is the complete problem. So this is, this class contains uncomputable problems. And so the main thing we're going to show you is that MIP star, which is the quantum counterpart of this MIP class, is actually equal to the halting problem, which is a big contrast from what you get classically. So that's the overall plan for these talks. In this talk, I'm going to focus on a certain technical ingredient that goes into our proof. And to explain sort of why it's necessary, let me tell you a little bit about just some challenges that arise when you, say, naively want to understand the complexity of MIP star. So if you wanted to understand this complexity class, well, there's two directions you might try to think about. One direction is to try to prove an upper bound on the class. What's the best upper bound you can place on this class with entangled provers? So as we saw in Andrea's talk, and as I'm sure many of you have seen, for these non-local games, it's often possible that using a quantum state, the quantum provers can do things that classical provers could not do, right? So one difficulty with that is that in general, there's no really good theory for, if I give you a description of a non-local game, to figure out how many qubits or what dimension quantum state might be needed for the provers to obtain an advantage over classical strategies. So we saw, in the previous talk, CHSH and Magic Square, these are games that use 1 or 2 EPR pairs and can obtain an advantage. But there's also games like this I3322 inequality that are constant size games. They look kind of similar to, say, CHSH, but we don't really know how these behave. And so it's conjectured that actually, the bigger the entangled state you have, the better you can do with this game. So adding dimension just strictly increases your winning probability. So that's a very simple game where we don't have a good understanding of how much entanglement might be necessary. So in general, this is this means that computing a complexity theoretic upper bound on this class is difficult. So what does that translate to in complexity terms? Well, the best upper bound you can get is just that for the class MIP star is you could write down, for any decision problem that's solvable in MIP star, there's the following algorithm which also solves it. So the algorithm, what it does is it just enumerates for all possible things that these two provers could have done. So all possible classical strategies, all strategies that use 1 qubit, all strategies that use 2 qubits, and so on, as you increase the dimension of the state. And you wait for this enumeration to find a good enough strategy for the two provers. And so since there's no a priori bound on how many qubits or what dimension of state the provers might need, we don't really know when this enumeration might terminate. And that's why you get this upper bound of RE here. So this is just like, for the halting problem, similarly, there's an enumeration, which is just to run, a Turing machine until the Turing machine until it halts. And again, you don't know how long that's going to take. So that's what results in the upper bound being RE. So this is what happens when you try to upper bound MIP star. And actually, since we ultimately show that MIP star is equal to RE, this upper bound is really tight, and I won't be able to give you any improvement on this. So in general, it will be the case that you'll need enormous amounts of qubits, like unbounded amounts of qubits to do well in these non-local games. So one point that I do want to make here, though, is that why is this issue of the number of qubits so important? Well, if you, instead of considering MIP star, where the two provers are allowed to use whatever entangled state they want, if you restrict the provers to use a state of a certain upper bounded dimension. So you say, the provers have to use a quantum state of dimension at most d, then you can show that you automatically get a bound on this complexity class that's something like n time of polynomial in d. So n time is non-deterministic time. So where does that come from? Well, that's just from this sort of enumeration, but it's using the fact that since you have this restriction that the provers are using a quantum state of dimension at most d, then you can write down a classical description of what they do in like poly d bits. And so then you can use this non-determinism to just guess a description of a good strategy, and that can be done in n time of poly d. So really there's the whole way you can get up to RE, to get beyond these bounds is you need to somehow deal with provers that use states that have that you can't put a nice bound on the dimension of. So to expand on that insight a little bit more, so I said that ultimately I'm not going to be able to improve this upper bound, that the upper bound is tight. So that means I have to show a lower bound that matches it. So I need to show that MIP star is lower bounded ultimately by RE. So how would you do that? Well, there's actually some challenges that are involved even there. In fact, even for much more modest goals. So you might, as a first step, want to show that MIP star is lower bounded by its classical counterpart. That this proof system that when you have quantum provers is at least as powerful as the one with classical provers, and that's not a priori obvious, because if you think about it, allowing the provers to share entanglement, we saw these examples of games where they can succeed with a higher probability than they can classically. In the complexity setting, that means that it might be easier for these provers to falsely convince a verifier that the answer to some computational problem is yes, right? Maybe the answer is really no, but they can use the entanglement to cheat the verifier and convince it to say yes. So some examples were actually found of protocols that are sound against classical provers, but don't work once you allow the provers to share entanglement. It was sort of a technically demanding thing to show even this lower bound that MIP star contains MIP. So you have to take a specific classical protocol and analyze the steps and show that they are, that two provers cannot cheat using entanglement. So if you want to improve this lower bound and you want to do better, so you want to show that MIP star contains a larger class of languages, then ultimately what do you need to do? You need to somehow design a protocol that uses entanglement, where the two provers are using entanglement in some way, because you want to go beyond this classical lower bound. But you want to make sure that they don't use that entanglement to cheat the verifier. So you have to somehow put constraints on what the provers can do with the entanglement. And more quantitatively, we can say the following, that if you remember from the previous slide about the upper bound, I said that if the provers are restricted to having a d-dimensional state, then we have this upper bound that's like n time of poly in D.
Anand,
So,
there was a question about this
sure.
statement, actually. Is this the best upper bound that we can get for optimizing over the d-dimensional states?
I'm not entirely sure. I think roughly it should be tight. Like I think we should roughly be able to show a lower bound that matches it, but I don't know exactly, whether like the polynomials match and so on.
Okay, thanks.
Okay, so I guess so the point I was trying to make is that so from the previous slide we saw this argument that if you have this if you have a d-dimensional state, then you have an upper bound. So if I want to get a lower bound on MIP star that's as strong as possible, I need to design a protocol that uses a state with as high a dimension as possible. And in particular, if I want to separate MIP star from the classical counterpart, MIP, which is at least I need to do to get up to here. I need to at least, separate it from MIP. I need to start by designing a protocol where the provers need to use a super polynomial number of qubits because they need to have a dimension that's bigger than exponential. So this is sort of the first step along the road to ultimately showing that MIP star is equal to RE. And that's the step I'm going to talk about in my talk. So in this talk, I'll tell you about a protocol that lets a verifier test that two provers share 2 to the n copies of the EPR state. So this protocol will be a self-test in the sense that Andrea defined in the previous talk. And this will also, go a long way. Ultimately, this will be the fact that it's a self-test will be useful for the complexity theoretic consequences. So in the talks tomorrow by John and Zhengfeng, they'll tell you how to use this protocol that self-tests these EPR pairs, as well as a bunch of other ingredients to actually design an MIP star protocol for the halting problem and ultimately show that MIP star is equal to RE. And maybe one point I do want to make about that now before I dive into the details is that why is this notion of self-testing important here? Well, it's related to this intuition that I gave you earlier that when you want to design a better lower bound for MIP star, you need a protocol that forces the provers to use entanglement, but in some specific way, that you want to prevent them from cheating the verifier by using that entanglement. And so the fact that the protocol I'm going to design here is a self-test is what lets you do this. It's what lets you prevent the provers from cheating the verifier. Okay, so with that said, I'm now going to switch over to telling you about how we're going to construct this protocol to test 2 to the n EPR pairs. Okay, so we already saw some definitions of this, but I'm going to review just to in case you weren't in the previous talk. So what is the this notion of testing EPR pairs that I want to use? Well, it's this very strong notion of self-testing, and how I'm going to define it is the following. So I'll say that a game is a self-test if it has the following properties. So first of all, the optimal strategy that 2 players can use in the game should be unique, up to sort of the freedom that you always have. So that means unique up to local isometries. So that means that Alice and Bob, when they play this game, they have to share a quantum state, and so that state has to be the state that's optimal has to be unique up to like local changes of basis. Alice can always rotate her part of the state if she does the same rotation on her measurements, and likewise Bob can do some local rotation as well. And you could never rule out such local rotations, so you have to always leave this freedom in. But up to this inevitable freedom of local isometries, we want to say that this state and the measurements that Alice and Bob apply are unique. And moreover, we want to say that this optimal strategy is also robust in the following sense. So any strategy for this game that achieves a success probability that's close to the optimum should itself be close to the optimal strategy. So what this means is, for instance, if I'm playing this game, this game is a self-test, and I observe that Alice and Bob succeed with a probability that's very close to the maximum probability, then that should imply that their quantum state is very close in some appropriate distance metric. So basically, up to local isometry, some version of this of the 2 norm, it should be close to this unique optimal state. So that's what we want to say for the state. And moreover, we want to say similar things for the measurements that Alice and Bob apply as well. So we want to say in addition that say when Alice gets a question X from the verifier, she's going to apply a certain measurement operator, which I've denoted AXA here. And that measurement operator as well should be close in this 2 norm up to isometry to the measurement operator that forms part of this unique ideal strategy. So this is the notion of self-testing that I want to use, and ultimately our goal in this talk will be to design a self-test in this sense, where the state psi opt here is 2 to the n copies of the EPR pair state. Okay, so right, so how would we go about designing such a self-test? Well,
another question just popped up, Anand, sorry.
Sure.
Ian asks, are there games with unique ideal strategy which aren't robust in the sense that you just described?
That's a good question, actually. I think I'm not aware of one off the top of my head. So the thing is that the robustness can depend on the dimension of the state. So you can have families of games where, you know, this 0.01 here would not be 0.01, but say 0.01 times some factor in the dimension, you know, polynomial in the dimension even. So for instance, like these parallel repeated CHSH games that Andrea mentioned are an instance of that. So, you know, that's robust. That's sort of not robust enough quantitatively for our purposes. So I would call that not robust. If you want to say, you know, is there like, you know, is there a game where you can place no bound at all over here? Then I'm not aware of one at the moment. Yeah.
Okay, thank you.
Sure. Okay, so right, so I'm going to tell you basically how to design, you know, a self-test for this, you know, 2 to the n copies of the EPR state. And the way we're going to do that is in a couple of stages. So we're going to start with a self-test for just 2 copies of the EPR state. And then we're going to sort of generalize the ideas. I'll show you sort of why that self-test works, why this will, you know, cover some ground that Andrea mentioned, but in maybe a little bit of a different language. And then I'll show you how to generalize those ideas to testing more EPR pairs. Okay, so this self-test for 2 EPR pairs, this is just the magic square game, which you'll have seen. So just as a brief refresher of how it works, you know, in the magic square game, the magic square is this 3x3 square here, whose entries are supposed to be, I guess in the notation I'm using, plus or minus 1 valued things. And so the way it'll turn into a 2-player game is that Alice will get, so this is, I think, a slightly different formulation maybe than what was used in the previous talk, is Alice will get asked for either a row or a column of this 3x3 square. Bob will be, you know, asked for a cell in the square, and they have to respond with an assignment to you know, Alice has to respond for the 3 variables in her row or column. Bob will have to respond with an assignment to the 1 variable in his cell. And so, for instance, you know, Alice might get asked for this row or that column, and then Bob will be asked for a cell that lies on Alice's row or column. And so, you know, they have to respond with assignments to these variables, and then they win if the following conditions hold. So first, you have these parity conditions that the rows have to multiply to 1, the columns have to multiply to -1, and Alice and Bob have to agree on the common cell. So, you know, you can check that there's no classical strategy that wins with probability 1 in this game, essentially because there's no consistent assignment to all the entries in the square that satisfy these parity conditions. And however, there is a perfect quantum strategy, which has value 1, and that perfect quantum strategy is the one that we're going to try to show is unique and robust in these senses. So what's the intuition behind this this proof? Well, I have to first tell you what a quantum strategy looks like. So in general, you know, a quantum strategy is going to look like something. So it's first going to consist of, you know, there's going to be a state that Alice and Bob have to share. And actually, you know, to satisfy this condition that Alice and Bob should always agree on the cell that they share in common, we're going to have them use the EPR state. And the EPR state has this nice property that if you perform the same measurement on both halves of it, you get the same outcome, essentially. So, you know, this will give you this sort of consistency condition for free. So that's why the EPR state shows up. And then to specify the rest of the strategy, you have to specify some measurement operators for Alice and Bob, when they're asked for these rows or columns or individual cells. And so the way the specification will be given is just, we'll specify a binary observable for every cell that satisfy the conditions that, well, first of all, every row or column should pairwise commute, just so that Alice can say measure everything in the same row or everything in the same column simultaneously. And secondly, the product of everything in a given row or in a given row should be equal to the identity operator. That enforces this condition that you get, this parity condition that the product of the outcomes on a row should be equal to 1. And the product of the observables in a column should be minus the identity operator. So that enforces this condition that the product of the outcomes should be equal to -1. And then finally, you have this thing that each row or column will pairwise commute, and that's just that Alice is able to simultaneously measure all the things in a given row or a given column. So this is.
We have one more question about this from Dominique. It's a rather long one. I'll read it out. He says he has a problem with the idea of the self-testing. So the guarantees that there is an EPR pair. So say that a game guarantees that there's an EPR pair. So that means that the state is an EPR pair up to a local isometry or local unitary, he says. But what if there's another strategy that uses 2 EPR pairs and just ignores one of them? That's not equal to 1 EPR pair up to unitary. And he asked, what did I get wrong here?
Very good. So this is a point that I kind of brushed under the rug. So this is why, in part, what we say isometry and not unitary. So actually, what I should have written there is, say EPR or the optimal state tensor some junk state. So the isometry has an output register and then a second register that can have any other state that you want. And the important thing about this junk state is, so actually you'll see it 2 slides from now, but I'll say a little bit more about it then. But so if you had like a second EPR pair that the provers just happened not to use, you could basically toss it into the junk state. And the ideal strategy should be such that or that it doesn't act on the junk state. So
okay, yeah. So this like second EPR pair that he's mentioning, it would just be the junk part.
That's right. Yeah.
Okay. Thank you.
Sure. Right. Okay, so that's okay. So on the previous slide, I sort of said what this ideal quantum strategy will look like, and then I specified in terms of some constraints on these observables, and so you can actually work out a set of observables that works, and these observables are just tensor products of 2 of the Pauli matrices acting on 2 qubits. So the state that Alice and Bob will share is 2 copies of the EPR state. So Alice has 2 qubits and Bob has 2 qubits, and then each of these cells is an observable that Alice or Bob will apply to their set of 2 qubits. So each cell is a 2 qubit observable, and those observables all have the form of being tensor products of Pauli matrices. So let's say this is an identity tensor of Pauli sigma x, which I've just denoted by x here. Like this cell is really like a Y tensor Y, and sort of for simplicity, I've written it as x times z tensor z times x. So you can check that these operators satisfy all of the conditions that I said on the previous slide, and they give you a valid strategy. So so that's the unique ideal strategy. And then what's the guarantee that you get as for this game being a self-test? Well, okay, this will maybe answer Dominic's question a little bit. So what you get is ultimately that if any strategy that succeeds in this game with probability greater than 1 minus epsilon, then what's true of it is that there's some local isometries, U acting on Alice's space and V acting on Bob's space, such that they take the state that Alice and Bob share and they map it to something that's close to 2 copies of the EPR state. So it's like the ideal state, tensor some junk state. So that's what they do to the state. And then for the measurements, they also map all of the measurements, all of these 9 observables here, to the corresponding entries in the ideal strategy. So for instance, observable number 2, if you remember from the the chart before it was supposed to be Pauli X tensor Pauli I. And so the statement that we have is that under the action of these local isometries, this observable number 2 gets mapped to something that looks like Pauli X tensor Pauli I acting on the EPR state, and then sort of identity acting on the junk state. So that's the statement that this game is a self-test. So how does one prove such a statement? Well, here's a little intuition. So if you look at this, ideal strategy, I said that there are these commutation conditions that within a given row or a given column, things have to commute. But one thing you can realize is that it's somehow essential that outside of a row or a column, if two things lie on different rows or different columns, that they not commute. Because sort of if everything commuted, then you could simultaneously measure all of the observables in this square, and then you'd get a classical assignment to the square, which is something that we know does not exist. So somehow this non-commutation idea has to be important here. And so the way that idea is going to be used is that we're going to try to actually, just from the condition that this set of observables satisfies the magic square, we're going to extract some algebraic properties that will hopefully pin down the unique strategy. So to formalize this is sort of the idea that of self-testing through representation theory. So the way it's going to work here is that we'll actually do the following. So as you probably know, that the Pauli matrices generate a group called the Pauli group with the following relations. So the X and Z operators are the Pauli X and Z matrices, and they're the generators of this group. And they have the relations that each of them squares to identity, and moreover that X times Z is equal to minus Z times X. So X and Z anti-commute. This is like an algebraic structure that you have here. Moreover, there's a unique unitary representation that's non-trivial in the sense that in this representation, minus the identity is distinct from the identity. So this is like the sign operator that this J that Andrea mentioned is non-trivial sort of means that this J is not equal to identity. But so this unique representation is essentially the standard one that you've probably seen. It's just the Pauli matrices acting on a qubit. So it has dimension 2. And moreover, the unique state that's stabilized by X tensor X and Z tensor Z, in this representation. So the unique state that's a +1 eigenvalue of those two things is the EPR state. So putting these facts together, if you wanted to show a self-test for the EPR state, one way you could do it is by somehow deducing from success in the game that there exists an irrep of the Pauli group in the Hilbert space of the two provers. And moreover, that the state that the provers use is stabilized by the representations of X tensor X and Z tensor Z in that irrep. Once you have that, since you know that this irrep is unique, you can basically extract the state out. So that's basically what we're going to do for the magic square. Actually, we have to do something a little bit more complicated because it's two EPR pairs and not one. So you have to use the Pauli group on 2 qubits, and that has a set of relations. It's essentially, if you just like generalize the 1 qubit relations in a natural way, this is what you get. So I won't really say too much about it. And this has the only non-trivial irrep has dimension 4. So this is how you can test for 2 copies of the EPR state. So just as a schematic diagram of how this proof approach works, it basically goes as follows. So the argument is I'm going to start with some strategy for the magic square game that succeeds with probability 1 minus epsilon. So from that, I'll construct, this strategy has some state and some observables, these A1 up to A9. So the first step in the analysis is going to be the following. So I'm going to construct some operators in the prover's Hilbert space that I'll write with tildes. So I'll construct tilted versions of all these 9 observables here, such that they're close to what the prover has actually applied. They're close to these untilted things from the strategy. And moreover, the tilted operators exactly satisfy the group relations of the Pauli group. So for instance, if you remember back from the strategy earlier, A2 and A4 were supposed to be basically the Pauli X and the Pauli Z acting on the first qubit. So they were supposed to be anti-commuting. So in the first step of this analysis, I'm going to try to construct an operator A tilde 2 and an operator A tilde 4 that are close to these A2 and A4, but exactly satisfy the anti-commutation relation. So this step, the way you can think about it is that you're showing that the structure of the magic square game itself, somehow the fact that you have these conditions that rows should multiply to 1 and columns should multiply to -1, that structure is testing the relations of the Pauli group, these kinds of relations here. Okay, so then in the second step, we apply this fact from the previous slide that there was unique representation. So once you have constructed these operators on the prover's space that satisfy the Pauli group relations, there's an isometry that maps them to the elements of the Pauli group, to X tensor I or Z tensor I or whatever the case may be. And then finally, to obtain so you can think about this as we're trying to, these sort of what we showed here is that these A's are like an approximate representation of the group, and we're rounding it to an exact representation of the group, and then mapping that to the canonical one, which is just the Pauli matrices. And then, sorry, I realized that this arrow really should be pointing at this here. So this is really what's doing the rounding. But anyway, you can ignore this if you would like. So once you've reached this stage here, so what have we done? We've constructed an isometry that maps the prover's operators to these Pauli matrices. And then finally, you can use this isometry plus the condition that you win in the game to deduce that the state psi was stabilized by this X tensor X or Z tensor Z, and that tells you that psi was close to being 2 copies of the EPR state. So this is sort of at a high level how the analysis of the magic square game as a self-test works. So I think this is a good point to ask for any questions. Okay, so if not, I'll continue. So what have I done so far? So I basically showed you how this magic square as a self-test for 2 EPR pairs works, but in this framework of representation theory. So ultimately, what we're going to try to do is, so I had some slides sort of showing you how the structure of the game, how to do this first step. So how the structure of the game implies these sorts of anti-commutation relations, but maybe I'll skip over these. So this is just sort of essentially if you work through the algebra of what these winning conditions mean, they can you can deduce anti-commutation from them. It's a little bit painful. But so now I'm going to tell you how to generalize this idea to many qubits. So I'll do this in 2 steps. The first generalization will be something called the Pauli braiding test, which will be able to test many qubits. It'll test basically n qubits, but sort of ultimately we want to get up to 2 to the n. So then in the second step, I'll tell you how to make this test even more efficient and how you can get to an exponential number of EPR pairs. So how do I generalize this? So okay, so first let me tell you what the result is for this Pauli braiding test. So the Pauli braiding test is a game, just like the magic square game, but with the following properties. So in the magic square, everything was constant size. Here, the questions that the verifier will send to the provers are now on the order of n bits long. The provers will still respond with answers that are on the order of 1 bit long, so there's a constant number of bits. And this game has quantum value 1. So there's a quantum strategy that succeeds with probability 1, and it's a robust self-test for n copies of the EPR state. So if the provers succeed with probability 1 minus epsilon, then there's some function of epsilon close to having this state. So how will it work? Well, it's going to use the representation theory of a bigger group. So it'll be the same approach, but just using a bigger group, and that group will just be the Pauli matrices on n qubits. So
Anand, we have a few questions. Sure. Probably took people a bit of time to type them up. So I have two questions for you. The first one is, do you have a good reference for the magic square self-test? Is it written down somewhere?
Yeah, so I guess the original reference is this paper by Wu et al. From 2015. I think Wu, Bankal, McCaig, and Scarani. Hope I'm not forgetting any authors. I think you can also find, like, I think, say the paper of Andrea, or like the papers by Andrea and Jalix, and also by myself and Matt Kudron, where we analyze the parallel repeated case. You know, we go through some of the same calculations. Like, I think there might have been a typo in one of the original papers, that like there's a signer that we tried to correct in the paper with Matt Kudron. So that's a reference that you could also look at.
Okay, great, thank you. Sure. And another question is, someone asks, the stabilizers of the EPR pair are Z times Z and X times X, but A2 and A4 are supposed to be close to X times Y and Z times Y. And I don't know what, that's the question. I think they're confused about this.
Sure. Okay, so I guess there's this issue of like what the tensor product symbol means. So when we talk about the stabilizer condition, okay, so maybe I'll say, like, you know, in this picture here of like what A2 and A4 are, this tensor product is across the 2 qubits that Alice holds, right? So Alice will hold 2 qubits, which are half of the 2 EPR pairs. And so this says, you know, apply X to the first qubit and I to the second. For the stabilizer relation, that tensor product was across Alice and Bob. So actually, I think I wrote what it is for 2 EPR pairs. Sorry, just here. So you know, for 2 EPR pairs, if you write out the full thing, it's, you know, you should be stabilized by, you know, Xi on Alice's side, tensor Xi on Bob's side, and likewise Ix on Alice's side, tensor Ix on Bob's side. So you basically check all of these stabilizer relations in the game. I hope that answered the question.
I think so, and otherwise they'll just ask again. Thank you.
Sure. Okay, thanks. Okay, so click back to where we were. Okay, so I was going to tell you about this, you know, n-qubit Pauli group. So the n-qubit Pauli group is really the natural generalization of the 2-qubit Pauli group, or the 1-qubit Pauli group that we already saw. So it's essentially the group that you get out of tensor products of these Pauli matrices. And I'm going to use this sort of nice notation for them to index these tensor products across n qubits. I'm going to just use a string or a vector in f2 to the n. So it's a binary vector of length n. And it'll just tell me, you know, which indices to put, say, an x, or which indices to put an identity. So this x of a means put an x on every qubit where a is 1, and an identity where a is 0. So in this notation, you can write out the relations you get when you multiply these x's and z's, and they have a very nice form. So remember, for the Pauli group, we had this notation, you know, x squared is equal to identity. You know, here in general, you can multiply 2 different x's that act on different sets of qubits. And what you find is that the indicator vectors that tell you what sets they act on just add mod 2. So that's essentially, you know, just a generalization of this x squared equals identity rule. And likewise for z's, if I take 2 z Paulis and I multiply them, then the index vectors will add mod 2. And then finally, if I try to take an x and a z and commute them past each other, I'll pick up a phase that goes as -1 to the inner product of a dot b, essentially because you get a phase from anti-commuting, you know, a z and an x whenever a and b are both 1 on a given location. So these are the relations of the Pauli group, and sort of just like, so I'm going to give them names. I'm going to call these first 2 relations here the linearity relations, and the last one the phase relation. So you know, just like for the basic Pauli group, the only non-trivial irrep had dimension 2, and it was sort of the canonical thing with the Pauli matrices. Here, the only non-trivial irrep has dimension 2 to the n, and it's also the canonical representation where you take tensor products of Pauli matrices. So what are we going to do to design this Pauli braiding test? Well, we want to do sort of exactly the same thing that happened with the magic square. So we want to figure out some sort of game, this Pauli braiding test, such that if a strategy to that game succeeds with probability 1 minus epsilon, then the operators used in that strategy all approximately satisfy these relations of the Pauli group. And then in our analysis, we'll show that once you have operators that approximately satisfy these relations, they're close to operators that exactly satisfy the group relations. This is the step that we called rounding to an exact representation. So for the magic square, this is a calculation that you could just do directly. For the Pauli group, for this n-qubit Pauli group, this is also a calculation you can do. But there's also a more general framework. So in fact, this sort of thing can be done for any finite group, and this is shown by Gowers and Hatami. So in general, when you have an approximate representation in a certain sense, you can round it to an exact representation. So then, once you've constructed this exact representation of the Pauli group on the prover's space, that lets you, construct an isometry to rotate everything to the Pauli matrices, and then by a similar argument as for the magic square, by this like stabilizer type argument, you can say that therefore the isometry takes the state psi that the provers used and takes it to be close to n copies of the EPR state. So this is the analysis that we want to hold. So okay, so what are the steps that so this step is just a mathematical theorem, and it's a fact about these approximate representations. Where do we need to use our quantum ingenuity? Well, we need to somehow construct a game that certifies these Pauli group relations and gives you the stabilizer relations you need to deduce the state. But really the tricky step is getting these Pauli group relations. So how is that going to work? Well, it's to do this, we're just going to really look at what these two different relations look like and design sort of a game that can test for each one of them separately. So first, I'll start with the easier case. So remember that there is this phase relation here, which whenever A and B have an inner product that's equal to 1, this is just certifying that this X of A observable and this Z of B observable anti-commute. So for this one, it turns out we actually already know a way to test an anti-commutation relation. That's exactly what the magic square game did. Remember, so one thing that we got out of the magic square is, for instance, that the the A2 entry and the A4 entry anti-commute. And so we can use the magic square to certify that any pair of observables that the provers use anti-commute in the following way. We just instruct the provers to play the magic square game, but using those particular observables as as what they use to measure that entry of the square. So we'll sort of measure. We'll play the magic square game, and then we'll identify the cell number 2 with this X of A observable, and cell number 4 with this Z of B observable. And then by success in the magic square game, that certifies that these two observables anti-commute. So we'll specify an A and a B for them, and we'll tell them play the magic square using these two observables, and if they succeed, that certifies the anti-commutation relation.
And what's the relation between psi and the calligraphic X and Z? That's a question in the Q&A.
So psi is the state that so psi and the calligraphic letters are all part of the prover's strategy that succeeds with nearly optimal probability. So psi was this thing that succeeded with probability 1 minus epsilon, and then these calligraphic X and Z's were the operators that they measured on psi during the game.
Yeah, so those are the kind of the real operators, and then the non-calligraphic X and Z are the ideal things that you would have wanted them to do.
That's right. Yeah.
Okay, thanks.
Sure. Okay, so the magic square game can already certify this kind of relation. It can certify this anti-commutation. Now the other class of relations was this linearity relation. And actually, there's already sort of a test for this kind of relation in the world of Boolean functions. So this is called the linearity test. So it turns out, there's this test that if you just have, actually, maybe it's easier if I just say it in the quantum case. So I'll just show you the quantum test, and I'll explain how it works. So essentially, there's this test that's already known for these kinds of linearity relations that can certify that if you have two, if you have a Boolean function f, then f of a times f of b is close to f of a plus b. And so it turns out that the same test, when you analyze it with observables, will certify these sort of operator linearity relations. So how does the test work? Well, it's basically the following. So if I want to check that Alice and Bob's calligraphic X observables satisfy this relation for particular A and B, what I'll do is I'll just tell Alice, I want you to measure in the X basis, and I'm going to ask you to measure X of A and X of B. So I'll send her X, comma A, comma B. And then I'll tell Bob X, I'll tell him the sum A plus B, and I'll give him a random, third vector C that's just as like a decoy, so he doesn't know that he's being sort of he's being tested against Alice. So Alice and Bob will get these things, and what they're supposed to do is measure the corresponding calligraphic X observables for the two vectors that they received. So for Alice, it would be measure X of A and X of B. For Bob, it would be measure X of A plus B and X of C. And then they'll respond with the outcomes. And then what we'll check is just that the product of Alice's two outcomes is equal to Bob's outcome for A plus B. And so the analysis that you can do is that if you do this test and you just do this check on the outcomes, then if you succeed with high probability, then the observables that Alice and Bob use to execute the test have to satisfy these operator equations up to some approximation. So this is how you test these linearity relations from the group.
So Ashwin is asking if you can elaborate a little bit about the mapping between these relations, these anti-commutation relations, and the magic square game. He says he's missing the correspondence between the two. So
sure. So let me scroll back.
I guess also about even just the single EPR pair then, but.
Okay, so okay, so for the magic square game for a single EPR pair, I guess sort of what you show in the analysis is that just from the condition that you succeed with probability close to 1, so that sort of means that it's like, let's say the product of these three observables is close to the identity operator, and the product of these three observables going vertically is close to minus the identity operator. Just from doing some algebraic manipulations on these equations you get, so you get an equation for each row, an equation for each column, you can deduce that say this cell here and this cell here are close to anti-commuting. So it's just some algebra you can do. And the way it's used here is that in general, if you want Alice and Bob to certify to you that the observables they use in response to certain questions are anti-commuting, what you can do is you ask them, you send them the questions that you want to certify anti-commute, and then you say, I want you to play the magic square using those observables to construct your strategy. So you'll then say, Alice, I'll give you a random row or column from the square, and Bob, I'll ask you for a random cell in that row or column, and I want you to measure, to execute the ideal strategy for magic square, but using the calligraphic X of A or calligraphic Z of B that I instructed you to use. And so because in the ideal case, the calligraphic X's and Z's anti-commute, they can indeed do this successfully, and then they can win in the game. And because of this property that I mentioned earlier, that if you succeed with high probability, you have to anti-commute. I mean, that certifies that the calligraphic X and Z used for these two cells will be close to anti-commuting.
Sorry,
maybe there's one
follow up on that.
Sure.
What I'm missing is why one can be, how we ensure that the players will follow the instruction to use these particular operators.
Very good. So that was actually the next thing I was about to say on this slide, is that you further want, so the question is essentially, how do you know they're using the same operators when you're testing for anti-commutation as they're using in the other test, right?
That's right.
So you essentially have to do a consistency sort of test, which is, to say that whatever calligraphic, thing they use in the linearity test was the same as in the magic square test. And so the way you do that is you just tell one player, you tell Alice that you're playing the linearity game, and you tell Bob that you're playing the magic square game. And you cross-check the part of their answers that's supposed to agree. So say you asked Bob for a row in the magic square, you check that the cell that was supposed to contain the Z operator is actually consistent with Alice's answer from the linearity game for that Z operator.
I see, thanks.
Sure. Okay, so so what have I shown you? Well, I said there was this approach to self-testing many EPR pairs through representation theory. What we needed to get that approach off the ground was a game that tested the relations of the Pauli group. And I've basically shown you how to construct such a game. So you need a part that tests the anti-commutation relations, a part that tests the linearity relations, and then this very important consistency test that I shouldn't have glossed over, that tests that that sort of links the two tests together. But so basically the Pauli braiding test is essentially running, you flip a random coin and you run one of these three possibilities. And if you succeed in this test, that implies that all of these relations have to hold, up to some epsilon error, and then you can turn the crank of the implications that I showed, a few slides ago, and use that to deduce the existence of a representation of the Pauli group, and therefore that the state is close to the EPR state. So this let us test n qubits using questions of size order n. And if you looked at the test closely, the way that n came into it is when you are specifying these a's and b's from the linearity test here. These are n-bit strings, and that's why the questions here have length n. So I see that I'm running quite low on time, so I'm just going to very briefly conclude with like a sketch of how you make this more efficient. So to make this more efficient, we want to sort of use the same framework with representation theory, but we want to get beyond this idea of just testing a single group relation at a time. So if you looked at the Pauli braiding test, sort of the individual subtests were either you picked a particular pair of things that were supposed to anti-commute and you tested that, or you picked a particular pair of things that were supposed to multiply according to the linearity rule and you tested that. Now in the Pauli group, there are 4 to the n group elements. And so just to specify, a pair of group elements will require like, n bits, which is, so that means if you want to test, 2 to the n EPR pairs, you need to specify 2 to the n bits to the provers, which we don't want to allow. So we have to somehow test many of the group relations simultaneously. And this is what the quantum low degree test does. So the way, the intuition behind it is the following. So there's an alternate perspective you could have for the Pauli braiding test, at least for the linearity relations, which is this, which is that when you're asking a prover to measure this Pauli x of a, one way you could think about that is that they could take their n qubits, measure all the qubits to get an outcome u, an n-bit outcome, and then compute the inner product of that u with the given index vector a. So that's the same, ultimately gives you the same outcome as measuring this observable x of a. You could interpret this whole procedure as saying, measure all the qubits to get this outcome u, and then return the 8th location of the Hadamard encoding of u. So the Hadamard code is an error correcting code that's just defined as the evaluation of inner products of u with all vectors. So this is a particular error correcting code with some nice properties. So it's a locally testable code and so on, but it has a very poor rate. So this string u gets encoded into all the possible inner products with all the possible a's, and that's sort of why the Pauli braiding test had this large communication complexities to specify one of these a's, which takes a lot of communication. So what if there was a code that sort of had a better rate, that could encode this U with fewer bits. So indeed, there is such a code. It's called the low degree code. Very at a high level, the way it works is that instead of encoding all the inner products of U with some vector A, you fit a low degree polynomial through points, so that its value at certain points is equal to locations in U. And then you evaluate that low degree polynomial at other points. So the encoding is just the evaluation table of this low degree polynomial. And so basically we, in our quantum low degree test, what we can do is replace the linearity test. So the test for these linearity relations with a test for this low degree code. And this is somehow much more efficient. And this lets you really test for 2 to the n EPR pairs with polynomial size questions. Or if you scale it down, it's n EPR pairs with log size questions. And so one way you can think of that is that really it's checking many of these sort of linearity type relations at once. It's checking many of the relations between different x observables simultaneously. And similarly, many of the relations of different z's observables simultaneously. And it's doing it by checking a carefully chosen subset of these x and z observables that comes out of this low degree error correcting code. So it's really the x's and z's that are indexed by, I guess, like columns in a generator matrix for this code. So I think I'm basically out of time. If people want to stick around, I'm happy to explain a little bit more how this test works. But essentially, you use the properties of the classical low degree code to sort of deduce many relations that you would have to check individually in the Pauli braiding test. So okay, that's basically concludes my talk, and I'll just leave up these 2 open questions. So the open questions are essentially to understand sort of the representation picture a little bit better, and also can we really push this approach to the limit and get, say, a test for n EPR pairs with constant size questions.
Great, thank you.
Thanks.
So if there's any questions, well, if you're a panelist, you can just unmute yourself to ask the question. If you're a participant, you can type it. Daniel asks, can you say something about what an approximate representation is?
Yeah, so an approximate representation is just a set of, let's say, unitary matrices. So for every element in the group, there's a unitary matrix such that the group multiplication rule holds approximately up to some norm, under some norm. So in our setting, the norm we're using is this funny thing called the state-dependent norm. So if I don't know if I can find it in my slides, but it's essentially saying, say for the Pauli group that we have an approximate representation of the Pauli group if, xz acting on the state psi is approximately equal to minus zx acting on the state psi, where the approximation is now in the 2 norm. But there are other notions, like you could just consider this in, say, the Frobenius norm, like the multiplication rule should hold up to some epsilon in the Frobenius norm.
I see. Thanks. I also have a question myself. In the meantime, other people can maybe type some stuff if they want. So you very briefly mentioned this low degree test at the end, but maybe this is getting ahead of the topic. Maybe it will appear in the other talks, but why do we need this if we're in a setting where we're essentially not worried about efficiency, like in this MIP star and RE, we're not worried about time complexity or number of rounds or stuff, right? So why do you want to have these tests be more efficient?
Sure, so it's a very good question. Actually, so this exponential efficiency that you test for through the NEPR pairs, that's not really necessary. But I guess what you will need is you need some sort of, I think you at least need some super polynomial efficiency. Like you need the number of EPR pairs that you test to be super polynomial in the number of bits that you send to the provers as questions. And I think John will get into that a little bit more, but essentially it's because in these protocols, you're kind of using these tests to like sort of expand randomness. Like you send some randomness to the provers as questions, but they have to generate more by measuring EPR pairs. And
I see. So you don't want to burn up your resources faster than you're generating them, essentially.
Exactly. So if you use like say the Pauli braiding test or like some parallel repeated CHSH test, you'd sort of like just like be chugging along in place. Like the amount of randomness you'd send in would all be used up and you get no more from the provers.
Okay, thanks. Laura asks if, so she says, the CSSH game also tests anti-commutation, so could you have gotten the same results by using CSSH in place of magic square?
Yes, so we could have. The only annoyance is that it's not value 1, so none of these games would be perfect completeness. And I think that the perfect completeness definitely makes the analysis a lot easier for the MIP star protocols. So that was, I guess, one reason to use magic square.
Okay.
I also had a question. So when you say that it's like the strategy is approximately close to this strategy that you want to self-test, I guess it is some sort of average closeness, right? Because if there is like one particular operator when just the provers just like decide to do some arbitrary random thing, then you might never test that particular one.
That's right. Yeah. So it's on average over the same distribution that you use to sample the questions for the provers.
Okay, and this is also this also holds for these approximate representations.
Yeah. So it's really that like on average the group relations hold. So if I pick a random pair of group elements and I check the group relation, that should hold on average up to epsilon.
Okay, thank you.
There's another question from Chinmay. He asks, hi Anand, can you talk about the relation between this PV low degree test, this Pauli braiding low degree test, and your games version of the quantum PCP theorem?
Oh yeah, so I guess that's a little bit of a long story. I guess the relation is ultimately that once you have, so this is an idea that goes back, I guess, really to this paper of Fitzsimmons and Vidic, and also some works by Zhengfeng Ji. But sort of once you have a test for EPR pairs that can test for Pauli matrices on those EPR pairs, then you can lift it to a test for code words of a stabilizer code. By if it's like say a 7-qubit the 7-qubit code or something, then this would be like a test with 7 provers. So it's like code words that are split amongst the provers. And the idea is that all of those code words look sort of locally like EPR states. Like they look, if I take the cut of like one prover versus all the others, then it looks like an EPR state. So you can lift these tests to test for code words, and then you can imagine designing protocols where you try to force the provers to share an error-corrected encoding of some state you care about, like say the ground state to a local Hamiltonian. And then you can both test that they have the state and also force them to execute measurements on the state. And so that's what went into this quantum games PCP. So we essentially came up with a protocol that made the provers share like an encoding of some low energy state to a Hamiltonian, and then we're able to efficiently measure the energy of this shared state.
Okay, cool. Thanks. One final question maybe from Daniel. He asks, any intuition on how to round to an exact representation? I'm not sure I understand the question.
Yeah, I guess maybe the best intuition that I have comes from thinking about the classical linearity case, actually. So the case where you just have a Boolean function and you want to say that if it passes this test that I showed that is close to a linear function. So that analysis you can think of that as like doing this rounding for representations of the abelian group Z2 to the n. And the way the proof works is by Fourier analysis over the group. So you take this Boolean function and you say that if it passes the test with high probability, then its Fourier decomposition, it has like one Fourier coefficient, at least one Fourier coefficient that's very large. And then that large Fourier coefficient is itself like an exact representation. Because like that Fourier coefficient gives you a linear function. So in general, the analysis sort of generalizes this where you take the Fourier transform over the group. And so the Fourier transform, like you find like particular representation in the Fourier decomposition that has a high weight, and that's how you do the rounding.
Okay, thanks. All right. Well, I think this ends the session then. So thank you, Anand, for the great talk. It was very clear. I know I learned a lot, so that's good. One announcement for tomorrow and Thursday for everybody who's still listening. We'll end at a different, or we'll start at a different time than yesterday and today. So the talks are going to start at 11:30 Pacific time. This is to accommodate for people in different time zones. So if you're in Europe, you have to stay up late or watch it the next morning. I guess if Anand wants to stay around, you can stick around to ask him some questions if you want, and otherwise, see you tomorrow. Thanks, everyone.
Thanks.